Hi, I am Chandrasekhar Gupta and we are discussing programming concepts. Today, we'll play a puzzle. Suppose if I have 3 boxes and an object, let's take a star, and I have placed a star inside any one of these boxes. Now, you need to identify which box is having this particular object. One of the approach which everyone tries to follow was, they'll go to the first box, they'll open and check whether the box is having object. If it is having the object, yes, I found the object. If it is not having the object, I'll try to move to the next box and the procedure repeats. They have named this approach as linear search. There is one more approach in which searching can be done, that is binary search. Suppose if I am having 8 boxes and these boxes are having a speciality that they will answer you with yes or no for a particular question that has been posed by you. If you ask the first box whether you have the object, it will say yes, I have it, or no, I don't have the object. What do you think are the minimum number of questions with which you will be able to find whether a particular object is having in a particular box or not? Think about it. In the case of n boxes, with the help of log n questions, you will be able to get an answer. Let's see, we are having 8 boxes. I will try to ask the first half whether you are having the object or not. The first half will say yes or no. If it says yes, I'll pick the first half and I'll ignore the second half. Now, I am having only the 4 objects. In these 4 objects, again, I will ask the first half whether you are having the object or not. Now, if it says no, I don't have the object, I'll ignore the first half. Now, I am left with only 2 of the boxes. See, now, I'll repeat the same procedure. I'll ask the first box whether you are having the object or not. If it has, it will reply with yes, or not, we'll try to ignore it. In this way, by asking only 3 questions, I have able to figure out in the case of 8 boxes. That is, we are trying to reduce the complexity by half at each and every stage. After having k iterations, the size of the input becomes n by 2 power k. And we'll stop whenever n by 2 power k is equal to 1. That is, after log n number of steps or after log n number of questions. In this case, this approach is called binary search, and this is how we will try to figure out most of the search operations in our programming language. But here, boxes are trying to answer you. In a similar way, binary search is having a condition that the array or the elements in which you are going to be searched, they need to be sorted. Why? Let's have a look. Let's try to understand linear search. Here, the element that has to be searched is 10. And let's call it as target. This is the array where we have to search for the element. We start with 0th index and we'll proceed till the last element, and we'll search at each and every element whether we were able to find the element or not. If we are not able to find, then the element is not present in the array, or if we were able to find the element in the array, then we will return its index. This exactly happens at linear search, and let's try to see how it can be implemented. If we just observe a particular task of searching or comparing an element at each and every index with the target is being repeated n times. So, as a particular task is being repeated again and again, I can use a loop over here. Let me consider a for loop. The for loop has to run n times. So, it starts with at index 0 and it has to proceed till n minus 1. I have to scan each and every index. So, I am incrementing it by 1 at every case. In every step, I am checking whether the element at that position is equal to target or not. If a of I equals to target. If I found the number, I can write yes, I found it, and I can return the index. If you observe, I is the index over here and I am trying to print the same value. If you try to look at complexities over here, we have worst case, best case and average case. On worst, if he is a pessimist, he may say that I may not find the element till I search till the last element. So, n iterations of this loop has to be repeated, and in the worst case, it can be given as order of n. If he is an optimist, he may say that I can find the element in the first index itself. In that case, the best case can be written as omega of 1. If we want to consider the average case, we can take the worst case plus best case divided by 2. Which is also equivalent to theta of n. So, if someone asks you about the complexity of linear search, it can be written as order of n. If you want to make an optimization over here, we can make it. Let's see how we can optimize linear search. Generally, here in this example, when I am trying to compare from the first till the last, suppose let's say at index 2, I found the element and this has been equal. I found the element and index has been returned. Now, after this, there is no point in searching the elements further. There is no point in repeating this task. The literal meaning is to come out of the loop and finish the job. So, if we are able to reach at this point, our job is done. And we need to come out of the loop, or else 7, 8 and 9 will be unnecessarily compared. For doing that, we have something called as break. Whenever you write break, if a program or control flow executes break, it will try to come out of the loop in which it was in. Here, it was inside this for loop and it will try to come out of this loop whenever the break statement is executed. As we have encountered break, let me give you a couple of examples where break can be used and how it can be accessed. Consider this case. Here, you are having a nested loop and you have written break over here. So, whenever I encounter break, I'll try to come out of inside loop, but still the outside loop will be processed. The break is enclosed only inside this for loop and only this for loop will be ruled out. Let's try to understand binary search. Consider this example. In this example, let's consider this is an array and you need to remember while you are working with binary search, the array needs to be sorted. Either it has to be sorted in ascending order or it has to be sorted in descending order. How binary search exactly works? Let's have a look. Here we are having left pointer and at the end of the array we are having right pointer. We will find a middle pointer which is equal to the ceil of half of left plus right. Here left is at index 0 and right is at index 6. The ceil of 3 is 3. We can have a middle pointer at this location. Now I'll try to get a target. Let's say if our target is 3, this is target. I need to find whether this is present inside this array or not. Let's see how this can be processed. Initially, I can compare the target with the middle element. As the array is sorted, if the element at this index, that is 7, is greater than 3. So, the scope of finding the element is only on the left side. As on the right side, all the elements are greater than 7, which is also less than 3. There is no point in searching the elements on the right side and we can search the elements only on the left side. In this case, I'll change the value of r and I'll make it point to m-1. Now, again I'll be calculating the middle, which is left plus right by 2, taking the ceil of it. That is 2 by 2, 1 in this case. Now the middle is pointing to this element. I'll check whether the target is equal to this. Yes, the target is equal. Then I'll try to return its index. If the target is still not equal, if the target is greater than, I'll change the left pointer to m+1, or if the target is less than, then I'll change the right pointer to m-1. You might have figured out the reason why we are trying to do as such. If we come back to the question of complexity, if we just observe, initially the size of array is n. We are trying to reduce it to half. After first iteration, we are trying to reduce that to half and so on. So, after k steps, the size of array is n by 2 power k. Now, we will stop the process or we'll stop this iteration when this is the required element or when it reaches to 1. Whenever we have reduced the size of the array to 1 or whenever we have eliminated all the other options except the required element that has to be searched, then we will stop the process. In that case, n by 2 power k is equal to 1. These are the number of elements. When it become only one element, we'll stop the process after k steps. If you just observe, k in this case can be log n to the base 2. As it includes steps, I am taking ceil of it. So, after log n number of times or after taking log n steps, I'll try to stop the process of this binary search. If someone asks you what is the complexity of binary search, then it can be log n to the base 2. We have seen about linear and binary search.